Can we just step back for a minute? So several weeks or maybe even months ago, I decided I was going to finally start talking about neural networks. And then I have been, kinda, because I started taking a bunch of tangents about things. Okay, let's just back up a bit, okay? Here's what I'm trying to do. Back in 2013, I was working as a biostatistician, and Dr. Judith James said, "Hey, Dustin, I got an assignment for you. I keep hearing about these random forests. Can you figure out what those are?" And I remember thinking, yes, I will do that. So I decided I was going to do that. I was going to figure out what these random forests were about. I assumed it was like non-parametric tests, like Friedman's tests or something like that. I thought it was going to be something stupid. And then I read about it and I said, whoa, these are awesome. And then I used them and I said, whoa, these are double awesome. These are amazing. And then several years later, I wrote my most cited paper. Sorry, correction, most cited first author paper with Juliana D'Onofrio, who was a graduate student. And I introduced a strategy that basically takes a random forest model and makes sense out of what the random forest model is trying to tell you. And of course, being me, it was based heavily on visualizations. So, I think I mentioned this already. When I came across neural networks, I was like, man, can there be a two-peat? P-E-A-T, like repeat, two-peat. Can there be a repeat of my luck earlier where I end up using neural networks in very clever ways that I find personally advantageous and then publish on them? And so far in the series, what I've tried to do is exactly what I did with random forests, where I use the random forest model to fit the data, and then I probe the model and use variable importance measures to try to figure out what the model is trying to tell me. And I started doing that for neural networks. And I got really bogged down in the details, and then I invented new ways of plotting things, and I invented new shout values, and the whole time I was really just trying to do what I did with random forest models. And I'm having second thoughts if that's the best approach. Because if I use the exact same method that I used for random forests on neural networks, have I really gained anything insightful? The longer I've been doing this, I don't think that's the case. So what I need to do, instead of trying to find a way to fit neural networks into my workflow, I instead look at what neural networks do really well and see if I can borrow some of that proficiency in ways that I can apply them naturally. And I think I know what it is. Now, you may remember when I started talking about neural networks, I talked about how neural networks develop these representations. And I used examples like this layer might encode shape, and this layer might encode color, and this layer might encode like, oh, that's a cat or a dog or a mouse or whatever. And the problem with all these layers and all these representations is we don't see them. We have no idea what kind of representations it's making. But it would be really cool if we could figure out what those representations are. And then I started to learn about autoencoders. And ladies and gentlemen, I think I may have found the answer to my question. I think I know how I'm going to use neural networks, baby. So we know that, again, these representations happen, and then at the end of the day, it's just predicting the next word if it's ChatGPT, or predicting a pixel location if it's an image, or predicting your outcome if you're using it for data analysis. But in the midst of that neural network, in the layers, it's developing these representations. So how do we gain access to those representations? Well, that's where autoencoders come in. So here's a representation of what an autoencoder is doing. Now, you might remember from an earlier video that a neural network starts with an input layer. So in this case, we've got variables x1 through x10. And these variables might be features from an image, or they might be variables in a data set. And just like before, those inputs feed into the first layer. And when you feed these variables into a neural network, the network starts building what are called nodes. And here these are labeled N1 through N6. And each of these nodes is basically like a little calculator, combining your inputs in very clever ways. And what's really happening is that your neural network is building representations. And basically what that is it's detecting patterns in your data, or features, or combinations of the variables in order to help it predict the outcome. Think of it like if you're trying to organize a drawer and you just dump everything out and then sort it into different categories. That's kind of sort of what these representations are doing. And you don't have to stop at just one layer. Neural networks can stack multiple of these layers. And each of these layers learns more complex or higher level representations based on whatever the previous layer figured out. So for example, the first layer might have picked up basic shapes. The second layer might have combined those shapes into representations of objects, and so on. And by the way, that's where the name deep comes from when you talk about deep learning. It means there are multiple layers, all stacked together. Now, normally with a neural network, all these layers work together to make a prediction. So after all those hidden layers, we might end up with an output node, let's call it Y. And Y could be whether there's a cat in the picture, or whether somebody clicks on an ad, or the predicted value of somebody's height. So that's how regular neural networks do, but we're going to do something different with autoencoders. Instead of focusing on predicting Y, we're actually interested in what's happening inside the network. Specifically, this middle layer here, which we're going to call Z, also called the bottleneck layer. And it's the compressed summary of everything the network has learned so far. So instead of making a prediction, like we normally do with neural networks, the network does something a little weird in order to figure out what those representations mean. It tries to reconstruct its own input. Or in other words, it takes these 10 original variables, squeezes them down into this bottleneck, and then builds them back up. Kind of like compressing a file and then unzipping it. Or another way to think about it is like if you were to vacuum pack your clothes and compress all your clothes into smaller bundles, the decoding part is like unzipping those bags and watching your clothes expand again. Except there's a slight difference here because there's going to be loss. Like when you pack for a trip, you don't like suddenly start losing socks or anything. But you do when you use autoencoders. There is going to be some loss of information. So why are we doing this? Well, the goal here isn't to duplicate everything. It's basically to try to figure out what are the essential features of your data. So if your network can take, let's say, 100 variables and squash those variables into 3 representations and still be able to reconstruct your data, or at least the most important parts of your data, that means those 3 bottleneck nodes, or in this graphic, Z1 through Z3, are capturing the real story underneath their data. So autoencoders are basically like professional summarizers. They help us find the most compact, useful representations of our data, while ideally throwing away the noise. So essentially, autoencoders don't just predict stuff. They teach us what matters about our data, and they do so by trying to compress our data and reconstructing it as efficiently as possible. So now imagine you have a huge box of crayons with 100 different colors. And then you draw a picture with 100 different colors. Okay, I know my image here isn't 100 different colors, but let's just pretend it is. Now what you do is you tell your friend to recreate the exact same image, but this time you give them only 5 crayons. Or another way to think about it is you give your friend a much smaller set of colors that can explain the entirety of the drawing. And so you describe the picture that you have colored, but you do so with only those 5 colors. And then at the end, your friend tries to recreate the image as close as possible, and then you compare the two, and then maybe you iterate, and then maybe try 5 different colors, or whatever. So that's exactly what an encoder does. It takes the really complicated thing, lots and lots of variables, and then it squeezes all that information down into a much smaller subset of variables. Then it tries to rebuild the original data with that much smaller number of variables. Or in other words, it's basically a neural network teaching itself what variables actually matter and how to combine them in a way that we still preserve as much information as we can. Now, chances are, if you have any experience with principal components or factor analysis, you might say, hey, man, that sounds a whole lot like principal components. Or, hey, man, that sounds an awful lot like factor analysis. And yeah, it kind of is. And the reason why they sound similar is because they basically have the same purpose. With factor analysis or with principal components, what you're trying to do is you're trying to say, all right, I've got these 100 variables or whatever. I want to see if they're really all representing the same thing. Do they share a lot of information in common? And so you might do a principal components or factor analysis and then decide, hey, out of these 100 variables, it's really just 3 major variables that are driving everything. And if we only include those 3 variables, we basically have 90% of the information that we had before. That's what we would call like an exploratory factor analysis or a exploratory principal components analysis. And from these, what we're trying to do is we're trying to infer the presence of a latent variable, or this super variable that causes our response to a bunch of smaller variables. And you tend to see this a lot in psychology, where you might be measuring depression and you have like 20 items that ask people basically the same thing. How sad are you? And all the different ways that sadness manifests itself in your life. But underlying that thing, we believe that depression is a single construct. And we ask a bunch of different questions to try to infer what the construct looks like. But here's the thing. Factor analysis and principal components has one major limitation. All relationships between variables must be linear. Yeah, that's a problem. Because if you have a complex relationship that is not linear, you're kind of dead before you started. But autoencoders are different. They use a totally different algorithm, and that algorithm allows, if not encourages, nonlinear relationships. So it can find like super nonlinear relationships. And so when you look at autoencoders, these bottlenecks, I'm calling them latent variables, or neural network factor scores. And once I started thinking of autoencoders in terms of factor analysis, that kind of broadened my view of what we can do with these. Because there's a lot of methods out there that we have to try to figure out what these factors mean. What do these latent variables represent? And if we can do the same thing with a neural network, that's pretty powerful. Except there's a problem. A problem that I am remarkably equipped to handle, my friends. That problem is factor analysis or principal components or structure equation modeling. All these are a class of models that we might call latent variable models. Latent meaning we can't observe them. So again, in psychology, we assume somebody has depression. We can't actually observe depression, but we can observe manifestations of depression. Because we don't know how they're actually feeling. We only know what they report to us, and then we use what they report to us to try to infer what their depression actually looks like. Now, I think you know me well enough by now to know that for me, in order for anybody, not just me, in order for anybody to understand a statistical model, they have to see it. They have to have a visual that informs them what the model is telling them. You could never, ever fully understand a model without a visual. No matter how many statistics you compute on it, you can compute the sample size, you can compute the skewness, the kurtosis, the mean, standard deviation, I don't care. No matter how many statistics you compute on it, until you see the data, you're not going to get what's going on. Which is why I've spent my career doing research in data visualization, because I want to understand what my models are trying to tell me. Now do you see the problem? If we are trying to visualize latent variables, like factor analysis or principal components or structure equation modeling, and the things we're trying to make inferences from the latent variables are unobserved, how in the world do you visualize that? Well, it just so happens that I have dealt with this problem before. A couple years ago, I wrote a paper, this paper, with a very funny name. I introduced a R package called Flexplavaan. And if you followed my channel, you recognize Flexplot, which is an R package designed to help visualize statistical models. What about Flexplavaan? Well, there's an R package called Lavaan, which stands for Latent Variable Analysis, I believe. And so Flexplavaan was an R package developed to visualize Lavaan models. And I think this is one of the more clever things that I've ever done in my career. I figured out very clever ways to visualize latent variable models. And one of the ideas, it's not the only idea, there's a lot of ideas in there, but one of the core ideas is that we treat visualizing these models just as we do with a scatter plot. When you plot a scatter plot, you plot each observed value as a dot, and then you plot the model or the fit or the implied relationship between the two as like a line, or maybe if you're using like a box plot, it might be a crosshair or something. You use some other symbol besides a dot. And so I started to think maybe we can do the same thing with factor analysis. That what we can do is we could plot, for example, a scatter plot matrix like this, where the diagonal elements represent the histogram of each of the variables, and then in the off diagonals above is just the simple bivariate relationship between two. So like in this plot, we have the relationship between potions and history. This is a fictitious Harry Potter data set that I made back at the time, by the way. And that's just a simple plot. That's just a simple scatter plot. We're just taking the raw potion scores and the raw history scores and doing a scatter plot. So what do those funny lines represent? Well, one of them represents just the regular regression line. Well, technically it's a lowest line. And then the red line is the model implied fit. And so using some fancy mathematics, that actually isn't all that fancy, you can read the paper if you want, I overlaid on these plots the fit that was implied by the model. And these plots I call trace plots. And then the lower diagonal is just residual plots. And again, that's just one example, but I created a bunch of different plots to visualize latent variable models. So as I started thinking about autoencoders, I thought, I know how to handle this, and I can use the same approach that I did before. Maybe, as well as some other ideas that I'll probably share next week. So just as a quick example, I wanted to see if this was possible. So I'm going to step into R real quick and kind of show you my screen and show you, I did this today. So this is not polished at all. I'm just going to show you what I've done so far. So all this first part is doing is it is simulating a data set that has 10 variables and 2 factors or 2 latent variables. And I simulated them using basically factor analysis theory. And I'm not going to go into details about how I did that. So then what I did was I built a neural network, but using autoencoders. And that's what all of this does. And so you can see that I am creating 3 layers. One is an input layer that compresses the 10 down to 6. And then we got the encoding dimension. And then we've got the bottleneck layer. And then I'm creating a decoder, which does the opposite. Anyway, I'm not going to go into details on this. So then what I decided to do is then I exported the bottleneck scores. So those bottleneck variables, each individual in the dataset has a score on Z1 and Z2. So I just captured that score. And then combined that with the original dataset, and then required Flexplot. And then this right here is basically what Flexplavaan is kind of sort of doing in the background with some asterisks. So I'm not going to go into the math. I will actually leave a link to a short paper that I wrote, not the official Flexplavaan paper, but another paper that I wrote that will explain how this process is done and why it's done. But then once you visualize it, so I'm going to visualize the relationship between our 2 observed variables, and I'm going to overlay the fit of the model. And it works. It's working. It's working! And what do I mean by it's working? Well, what I'm seeing is I'm seeing a line that passes through the center of the data, the observed relationship between V1 and V2, and that line is a direct representation of the autoencoders because of the fancy math that I did earlier. Or in other words, I think this is going to work. But unfortunately, that will have to wait until next time because that's going to require a lot of R programming on my part to get that to work. But that's okay because I'm excited about it. And what is the end result of this? Or I guess, what is the implication of this? Let's say this ends up working out. So what? Big deal. Yeah, it kind of is, because factor analysis has always had this limitation that you have to assume linearity. And there's different ways that people hack it, but they've never been satisfactory. And they're just hacks. But the cool thing about neural networks and autoencoders is they're not hacks. They are literally fitting a good relationship. They are literally finding representations. And so I see massive implications for this. And here's another thing that I realized. So it's interesting, that Flexplavaan paper, I thought it would be groundbreaking, but it really wasn't. Not as much as I thought it would be, at least. Because, like, I don't know, like, in my mind, the whole point of that paper was, what happens if you have nonlinear relationships? How would you even know? And before my paper, there really weren't good ways to know if there were nonlinear relationships between your latent variables and your observed variables or something like that. But now there's a way to know. But unfortunately, in that paper, I didn't offer, in that one paper, a good solution for how to correct it. I did offer one in a document that I'll link below, but it was like a really convoluted way to do it. But the cool thing about neural networks is it just naturally does it. It's kind of like random forests. Like with regression models, in order to fit nonlinear relationships, you really have to hack them to make it work, and you have to know which variables to hack to make it work. Whereas with random forests, it just does that naturally, and that's the exact same thing with autoencoders or with neural networks. They naturally find these nonlinearities already, and so you don't have to hack anything. You just let the algorithm run. And so if we can use this to detect nonlinearity in a factor analysis model, that's a game changer. And I also see implications. I actually had a project started probably about 5 years ago where my student and I had like 400 items from a questionnaire on schizophrenia risk. I'll leave a link in the description if you want to see the papers that we've written on that. And so the idea behind those two papers, I think, one or two papers, I mean, his thesis and his dissertation, the idea behind those papers was we're going to take these 400 items and try to figure out if there is a much smaller subset of those items that are really predictive and everything else is just redundant. And I invented an algorithm called SEMBAG, clever name, but I don't know how effective it was. But I would really like to use neural networks for this sort of situation where you've got lots and lots and lots of variables. And you can feed them into a neural network and then figure out what is really the essential elements of these hundreds of variables. And what do those representations mean? And can we use those representations to model an outcome in a way that helps us understand what our data are really telling us? That's really what I'm trying to do. And if I can figure it out, that is cool. But who knows? Maybe I'll fail. I have done plenty of that. But in the meantime, if you want to take a stats class from me, I am starting a new sequence, starting with introductory simplistics, and then following that up with a visualization / data mining course, and then following that up with a mixed model class. So if you're interested in beginning that sequence or just taking an introductory simplistics class from me live through Zoom, see the link in the description. Or if you want to do it all on your own, I'll leave links for those classes where you can do self-guided classes instead. Anyway, so I hope you will join me, where next time I'm going to see if these tools actually work. Peace out. Ooh, can you see me? Wait, do they not drop leaves in Florida? ChatGPT can do that? What? One would say I am an interaction expert. It's like we statisticians could not decide what should have a variance, so we just decided everything has a variance, damn it. You want a variance, you're gonna have a variance, all right? Because we demand variances everywhere. Can you believe that? I don't think that's going to make the cut. I have children in my audience. Dashboard, community. No, you're not. I'm a native Italian man, I swear. You're just trying to steal my algorithm so you can market it? Exactly. Yeah, y'all are trying to distract me here. That's the problem.